Good afternoon, all of you. Okay. Good afternoon, all of you. So in the yesterday's class, we have discussed about common emitter configuration, common collector configuration, and also we have differed between the common base, common emitter, and common collector configuration, right? So by the end of that concept, we have completed the bipolar junction transistor, nothing but a BJT. So we have completed the concept of BJT, that is almost 70% of the fifth unit is completed. So we have left with only one concept, one important concept, that is FET, that is the field effect transistor. Okay, that is field effect transistor. Just give me 1 minute. So there is actually the field effect transistor. So let us discuss about the field effect transistor in the today's session. Okay. Why we are going to call it as a field effect? We will try to analyze that one. See, this is, we are going to call it as a field effect transistor. So that is it. So usually bipolar junction transistor is a current controller device. That is, when you are controlling the current at the input side, that is either the base current or the emitter current. Whenever you are controlling the input current, the output current is also going to get controlled, right? But for that reason, we are going to call the bipolar junction transistor as a current controller device, right? But whereas here, this is the field effect transistor. That is, this is actually a voltage controller device. That is, whenever you are controlling the field, or whenever you are controlling the field, especially, therefore the transistor operation will be get controlled. That indicates that the current will be get controlled. The output current can be able to control by controlling the field of the input voltage or the gate voltage. Okay, that indicates the field effect transistor. That is, this transistor is going to get affected due to the field. That field is nothing but an electric field. That electric field is nothing but an gate voltage. So this is actually the named it as a field effect transistor. Yeah. So here we have two different types of field effect transistors. One is a junction field effect transistor, JFET, metal oxide semiconductor field effect transistor. We have two types of field effect transistors, JFET and MOSFET. Okay, it is a junction field effect transistor. This is a metal oxide semiconductor field effect transistor, MOSFET. So again, in JFET we have an N channel and a P channel, and in MOSFET we have a depletion type, enhancement type. So these are the two types of MOSFETs. And again, in depletion type we have N channel and the P channel. Again, for enhancement type also we have N channel and P channel MOSFET. Okay, so that is depletion type N channel MOSFET, depletion type P channel MOSFET, enhancement type N channel MOSFET, enhancement type P channel MOSFET. So in our syllabus we are not going to discuss about the MOSFET. So we are going to concentrate mainly on this JFET. Okay, that is nothing but a junction field effect transistor. So that means we need to discuss about the N channel JFET and the P channel JFET. So usually if you want to understand about the operation of a FET, means that indicates that you need to understand the operation of JFET. Okay, so in the syllabus he didn't mention especially the MOSFET. So for that reason we are not going to discuss MOSFET. We are going to discuss only the JFET. Okay, now how the FET symbol is look like. Okay, rather than symbol, what are the terminals of a FET? We will see here. See, we have 3 terminals, that is drain, source and gate. So we have 3 terminals, that is, we are going to call this as a drain, and we are going to call this as a source, and this terminal is a gate. So FET will have 3 terminals, just like BJT have 3 terminals. What are those 3 terminals? Base, emitter and collector. Similarly, the FET will also have 3 terminals, drain, source and a gate. So the voltage which is applied between the gate and source is called as a VGS, that is gate source voltage. Okay, and the current which is traveling from the drain is called as a drain current, ID. Okay. So based on the current flowing in the channel, we have two types, that is N channel and a P channel. Okay, so that is, I will show you here. Here we have a configuration as N channel and P channel. So depending on the current flow, in which channel the current is flowing, either it is an N type or a P type. If the current is flowing in an N type, then we are going to call it as an N channel. If the current is flowing in a P type, then we are going to call it as a P channel JFET. So usually, see here, here we have three. Here we have, this is actually N channel JFET. So this is a gate and this is a source. This is a drain. This is a contact, that is nothing but a connection between the drain to this transistor. So this is actually N. Okay, this is N. So where the current will always try to flow from source to drain. Okay, the current which is going to flow from source to drain. Okay, nothing but an electrons which are going to flow from source to drain, but the conventional current direction will be always from. So this is actually the flow of electrons, but the current direction will be always from drain to source. Clear? So the flow of electrons is always from source to drain, but the conventional current direction is from drain to source. Okay. So the current is flowing through the N channel, and this is actually the P type of semiconductor and the P type of semiconductor. This is nothing but a depletion layer. Okay. This is a depletion layer which it is going to form. So this is N channel. Similarly, here we have a P channel. We are going to call it as a P. In the previous case, we have N here. Here we have a P. Okay. So this is a P channel JFET. So this P channel JFET is the same thing, but in this case, the current will flow from source to drain. Here, the current direction will be reverse. Okay. It is not going to flow from drain to source. It is going to flow from source to drain itself. That is, the conventional current direction is drain to source. Here the conventional current direction is not drain to source, but it will be source to drain. Okay. So for that reason, the gate symbol will be reverse in the P channel and N channel. Okay. You can see here the symbols. See here. See N channel JFET. The current direction, that is arrow, will be like this for a gate, but for a P channel it will be away from the gate terminal. Okay. So this indicates the N channel. There is no difference between N channel and P channel. Only the direction of a current in the gate. Okay. Which if it is entering into means we are going to call it as an N channel. If it is leaving from the gate means we are going to call it as a P channel JFET. So coming to this is actually the construction of an N channel and a P channel. So we are going to have N type of semiconductor, where the area will be so much of large, but P type of semiconductor area will be very less. Okay. And we are going to connect the gate terminals from this P type to P type, but for this N channel we are going to connect the drain and source. Okay, we are not going to connect the gate to the P type. Sorry, gate to the N type. We are connecting only the drain and source to the N type, and to the P type we are connecting the gate terminal. Okay. By using this gate terminal itself, we are going to control the voltage. Nothing but we are going to control the current. Okay. Just I will. So the same thing here we have discussed here. If you see, so phase is divided into N channel JFET and the P channel JFET. Similarly, this MOSFET. So it consists of an N-type bar, which it is made up of silicon. This is N-channel JFET. Okay, this is a drain, ohmic contacts, and gate, source, and depletion layer. Which this gate is connected to the two P-type of semiconductor materials. Right. Now, coming to the source, that this terminal which is connected to the negative pole of the battery. That is, you are going to connect this one to the negative pole of the battery, and drain you are going to connect to the positive terminal of the battery. Okay. So electrons which are majority carriers. See here, whenever you have connected the positive terminal of the battery, what happens? All the electrons will try to move from this point to this point, and all the electrons will repel at the source point. Right. For that reason, the electrons flow will be in this direction, source to drain. So drain, this terminal is connected to the positive terminal of the battery. Majority of the electrons will leave from the bar. Okay. That is, electrons will move from source to drain. So gate is a heavily doped P-type of silicon material, which it is connected between the N-type, that is, which P-N junctions are formed. Okay. So this one, P-N junction, P and N junction. So we are going to connect the gate here, and again we are going to connect the gate here. Same common terminal. Okay. So we are going to call it as a channel depending on the current direction. Either the current direction is in N, then we are going to call it as an N channel. If the current direction is in P, then we are going to call it as a P channel. Coming to the principle of operation, let us discuss about the principle of operation. If you see clearly here, we have not applied any voltage. Okay, we have not applied any voltage here. That is VGS, gate to source voltage is 0. So now what we are doing, we are connecting the positive terminal of the battery to the drain and negative terminal of the battery to the source. So when you have connected the positive terminal of the battery to the drain, negative terminal of the battery to the source, what happens? All this is actually an N type of semiconductor. Therefore, all the majority carriers of electrons will try to attract towards this positive terminal, and it will get repelled towards this negative terminal. Therefore, this is actually the direction of electrons, right? This is actually the direction of electrons. But whereas this PN junction, this P2N junction and this P2N junction will be reverse bias. Okay, this P2N junction, whenever you have connected this voltage, this will be get reverse biased with respect to this applied voltage. We are going to call this voltage as VDD or VDS. So we can also call this as a VDD voltage or VDS voltage also. VDS voltage is the voltage difference between the drain and source. VDD is the voltage which you have connected to the drain terminal. So now, but if you see clearly what happens, here the current direction is reversed. This is actually the conventional current direction, which you already know, which it is opposite from the electron's direction. Okay, if the electrons are flowing like this, then the current direction will flow in an opposite way, conventional. Now what happens? So whenever you are increasing this voltage, so we have a depletion layer here. So whenever you are increasing this voltage, this depletion layer will also increase. Whenever you are increasing this voltage, this depletion layer is also increased. Therefore, this current flow could also able to get controlled. Okay, so we are going to call it as a voltage controlled device. But when you are making this gates to source voltage as 0, for example, if you doesn't want to vary this voltage, you could also able to vary this VGS, and you can also able to control this voltage. Okay, that is actually the main advantage by using this JFET. Oh, so this is actually the flow of current direction. So when the current is flowing and when VGS is equal to 0, we have a depletion layer because of the reverse bias of this PN junction, and the current is flowing from source to drain, and the conventional current is flowing from drain to source. So this is just like a tap. For example, if I have a tap, just I will draw it. If I have a tap, okay, we have a tap. Water is flowing here, but this flowing of water is nothing but an drain. Okay, nothing but those are electrons. This is an source. Okay, so this controlling terminal is nothing but gate. Okay, so we have a water, but to allow the water, you need to open this gate. That is, you need to open this gate. Then only the electrons will move from drain to source. Okay, then only the electrons will move from drain to source. That is, you are controlling this electrons flow by using this gate. Okay, for example, if I have not applied any voltage to this gate, then normally the electrons will flow. There is no problem regarding the current. If you want to control the current, then you're going to apply the voltage to this gate. See here, if you see, we have a voltage here. We are going to call these are nothing but an output characteristics. Okay, these we are going to call it as an output characteristics. Okay, so what is the output? Output voltage is a VDS, and output current is the drain current. Drain current is output current, and output voltage is the voltage difference between voltage difference between the drain and the source. So this is the current that is the saturation current, that is maximum amount of current where the N channel or where the source could able to transmit to the drain. Okay, we are going to call this a maximum amount of current. So it could able to deliver the maximum amount of current, and when you are varying this VD, this depletion layer will increase. See here, see this is a VDS. Please all of you listen carefully here. So this is a VDS is nothing but this voltage. Okay. So you are increasing the voltage. So whenever you are increasing the voltage, the current is transferring, but similarly the depletion layer is also increasing. Okay, the depletion layer is also increasing, but the current transfer is also increasing. So you are increasing the voltage at position 1, and again you are increasing the voltage at position 2. At position 2 also current is increasing, but still the depletion layer is also increasing. Okay, we didn't make the voltage as a constant. We are increasing the voltage means the electrons push up will also increase. Okay, the velocity of the electrons will also increase, so it will try to move more, but the depletion layer is also increasing. So that indicates up to the position, up to this position 3, what happens? The depletion layer will increase, the current will also get increased. But at this point, that these two depletion layers will be in contact with each other. And see here, these two depletion layers will be in contact with each other when you are increasing this VDS voltage completely. At one point of voltage, at one value of voltage, what happens? These two depletion layers will get increase, and at one value of the voltage, these two depletion layers will be in contact with each other, and we are going to call that as pinch off. And we are going to call that value of voltage at which the pinch off is taking place is called as a pinch off voltage, that is VP. That is the voltage, the voltage is called as a VP. So after that VP, what happens? The maximum, that is, it is reaching the saturation point, that is, it is reaching the maximum amount of voltage. After that voltage, if you increase also, the current increase is not going to take place, it will remain constant. Okay, it will, sorry, the current transfer will remain constant after, if you are varying this, you are varying the VDS after the pinch of voltage also, right? So that is nothing but this condition. Okay? So you could not able to think that if you have a depletion layer, the current flowing will be a constant. Okay, it could not able to get the more amount of current. Okay? So then after, what happens? This is called as when VGS, that is when the gate to source voltage is equal to 0. The same condition we have seen here. Okay, I will explain with respect to that also. See here. See, when VGS is equal to 0, if you see with respect to the class notes, when the VGS is equal to 0 and VDS is equal to 0, then both are the 0. So we have only two voltages. One voltage is VDS, that is this voltage, and one voltage is VGS, that is this voltage. So we have only two voltages which we could able to change, or we could able to vary the voltage, right? So now what am I doing? When VGS is equal to and VDS, both are 0. So when both are 0, what happens? It is not going to take place anything. The current transfer is not going to take place anything. So no voltage is applied between the gate and source, drain and source. The thickness of the depletion layers will be uniform. That is, there is no change in the depletion layers because you have not applied any voltage. That indicates either it is a forward bias or either it is a reverse bias. Neither it is a forward bias nor it is a reverse bias. Right? Now coming to the next one. So when VDS is equal to 0 and when VGS is decreased, okay, so you are making VDS is equal to 0. That is, when you are applying the voltage, whatever you are applying the voltage is 0, and when VGS you are decreasing from 0. That is, you are applying the negative voltage. You can see those characteristics here. See, you are applying the negative voltage, that is 0 to -1 volts, -1 to -2 volts, -2 to -3 volts. Okay, whenever you are that is decreasing the VGS voltage, what happens? The PN junction will be more reverse biased. You see clearly here also. If you see clearly, if you are applying the negative terminal of the battery, we also have this one circuit diagram. See here. If you see here, we have applied the -1 volt. So that means you are applying the negative terminal to the P type, okay, and this positive terminal to the source. So when you are connecting the negative terminal to the P type, what happens? The depletion layer will start increasing. Because all the holes will be get attracted towards this one, the depletion layers will start increasing, means you are increasing the reverse bias voltage. Okay, so this PN junction will be reverse biased, and the thickness of the depletion layer will increase. Okay, as VGS decreased from 0, reverse bias voltage increases, and thickness of the channel will also increase. Okay, and we are going to call that as a cutoff region. We are going to call at one point of voltage as a cutoff region. So now when VGS is equal to 0 and when VDS is increasing, that is the thing what we have discussed now. When VGS is equal to 0 and when VDS is increasing, what happens, only the VDS is increasing. So what happens, this reverse voltage will continue, therefore it will increase the depletion layer when the VDS is also increased, and at one point of time it is going to touch together. We are going to call that voltage as a punch off. And see that one, this is actually a pinch off voltage where two depletion layer will be in contact, and therefore the current will be in a saturation. So this is the thing, the current will be in a saturation after the pinch off voltage. So this is the operation of three conditions. The first condition is when VGS is equal to 0, when VDS is equal to 0, nothing is going to happen. But the second one is when VGS is equal to 0 and when you are increasing the VDS. Okay? And the third one is when VDS is equal to 0 and when you are reducing the VGS. I'll write here. First one is when VDS is equal to 0, VDS is equal to 0. Right? For this condition, it is not going to, every depletion layer will be at its original uniform, that is original area only. It is not going to neither increase nor decrease its area. Now, when VDS equal to 0, VGS is decreases. Okay, decreases means 1 volt, like that. That is, you need to decrease the gate voltage. You should not increase the gate voltage. If you are increasing the, that is, if you want, means you could also able to increase the gate voltage, because if you are increasing, what happens, this depletion layer thickness will get decreases, so that the more current transfer could also able to happen. Okay, just like a tap. Okay, now that is the condition when VDS is a positive voltage. Okay, you need to increase the voltage, not decrease, when VGS is equal to 0. So these are the three conditions. Okay, these are the three conditions, especially these two conditions, where the JFET is going to work. Okay, so whenever you are decreasing the voltage, the reverse bias is going to be more reverse biased. So whenever it is going to be more reverse biased, the depletion layer will be get increased. So when the depletion layer will be get increased, what happens to the saturation level of the current? This current will also decrease. Okay, so whenever still you are increasing that, still you are decreasing the VGS voltage, still this current magnitude is decreasing. That means you are controlling the current by using VGS voltage. See, this is at position 1, this is at position 2, position 3, and position 4. So when you have applied -3 volts, what happened? It is going to get, and still if you are applying the voltage which it is equal to the pinch of voltage, what happens? It is the current, what it is going to be 0 completely. Okay, see here that the drain current is completely 0. So that means it could not able to transfer any amount of current, because you are increasing the voltage, you are increasing the voltage, you are increasing the voltage. At point of time you are increasing, I'm sorry again. So you are decreasing the voltage. VGS means you are decreasing the voltage, you are decreasing the voltage, and you are decreasing the voltage. At one point of time, that voltage is equal to the magnitude of the pinch of voltage, and the current transfer will be equal to 0. There will be no drain current, the drain current will be equal to 0. Okay, this is the operation of JFET, and this is actually the output characteristics. Okay. So the same thing explained here. So we are going to call the channel as also resistor, because it is acting with respect to resistor only. Okay, whenever, if the resistance is high, what happens? The current flow will decrease. If the resistance is less, what happens? The current flow will increase. For that reason, it is also renamed as a channel, as a resistor. Depending on the area, the current transfer will be, it is going to depend on the area. If the area is increasing, the current transfer will increase. If the area is decreasing, the current transfer will decrease. Okay, this is actually the symbol of an N channel JFET and the P channel JFET. So these are the, I think, see here, I will show you the characteristics, but here these are the characteristics, but we will discuss this one in the next session. Just I will repeat again what you have discussed. Okay. Okay, FET, we have two types, that is okay, we have two types of FETs, that is JFET and MOSFET. Okay, in the JFET we have N-channel JFET and the P-channel JFET. In the MOSFET we have a depletion type and also enhancement type. Every type will also have N-channel and the P-channel. Those channel we are going to call it as depends on the current flow. Okay, we have a drain. We have three terminals: drain, source, and gate. With respect to the applied voltage and with respect to the gate voltage, you could able to control the current, the value of the current. Okay, this is the symbol of N-channel and P-channel JFET. Okay. So this is actually the construction of the JFET, which it consists of N-channel. This is actual N-channel JFET. So we have a P, and we are connecting the gate terminal common to the P and P. We are connecting the gate channel common to the P and P. Okay, and then after, so the current will always flow through the source to drain. Drain is connected to the positive terminal of the battery, and source is connected to the negative terminal of the battery. So always the gate voltage you need to decrease, and the applied voltage you need to get increase. Okay, so this is the drain voltage, and the voltage difference between drain and source is called as a VDS, and that is actually the output voltage. And this is the gate, and here we have considered the gate voltage as a 0. For that reason, it is short circuited. Okay, so this P and P we have connected together. And this is nothing but you are applying, whenever you have applied this voltage, this makes the PN junction as reverse biased, and whenever you are increasing this voltage, this depletion layer will also increase. So this is actually the current flow, and so whenever you are increasing this voltage, the current is going to flow from drain to source. The current is going to flow from drain to source. That's not a problem. And it is going to flow, the current flow will increase, but at one point of voltage it will start increasing, and that voltage is called as a pinch off voltage, and it will remain completely constant, B4 stop messaging like this. Respond B4. 1B4. Okay, I have remembered your roll number, don't forget. And these are the output characteristics. Output characteristics consist of saturation region, ohmic region, and also this is called as a cutoff region, not mentioned here. This is called as a cutoff region. So we have three regions: saturation region, which the current will be completely constant; cutoff region, that is where the current will be equal to 0; ohmic region, where you can able to find out that is just like a ohmic resistance characteristic. If we see the characteristics of a resistance, it is a linear characteristics. So for that reason, we are going to call it as an ohmic region. Okay. So whenever the VDS is equal to 0 and VGS is negative, that is whenever you are decreasing this VGS, what happens? This reverse bias voltage is increasing, and therefore the current transfer will also increase. Current transfer will decrease. Okay. When VDS is positive and VGS is equal to 0, what happens? The current transfer will increase. So this is the where we are going to connect the VGS as a negative voltage. Okay. So this FET is actually the very last concept in our syllabus. Okay. If you have any doubts, you can ask me. Tomorrow we'll discuss about this characteristics, volt ampere characteristics. The same thing, but we'll discuss more elaborately. Okay. With respect to this circuit diagram, we'll try to discuss. This is actually the introduction of a FET and the principle of operation of a FET under the three important conditions and the construction of a FET. Okay. I think who is there now? So yesterday I have sent you the assignment, I think, through your CR, through Hassan. Okay. So whatever the attendance, sorry, only 2 or 3 members have sent me the document. Please send me that your written PDF document by tomorrow. Okay. So by tomorrow evening, I need to receive all the documents. Please send that document to my WhatsApp number. I think you already know my number. And give the file name as BEEE assignment, BEEE and your roll number. If not, when you're sending your document, send me your roll number also. Okay. Who will send me attendance? Hassan, are you there? I think Hassan is not there. Okay. Who will send me attendance? Any CR is there? Please all of you go through all the concepts and prepare perfectly for the exams, because after completion of this April 30, JMT also have given, I think you already know, by April 30 we need to complete the syllabus, and I think they will plan for mid examinations as well as external examinations also. For external examinations also, I think they will not give you any holidays, okay, practice holidays. They will complete the exams and then after they may give you holidays. So please all of you prepare this subject thoroughly, and this is the new subject. So almost we have covered every concept. Okay, whatever the concepts we have not covered, we will discuss at the last. Ashwita, are you there? If you are there, can you send me the attendance? Raise hands who will send me the attendance. Raise hand, because I want response. If I am not receiving attendance means. Okay, right, Ashwita? Send me the attendance, okay? Okay. Please, if you have any doubts, please ask me. We'll discuss more elaborately regarding this VA characteristics. That is, these characteristics. Okay. We'll discuss more elaborately about these characteristics in the tomorrow's hour with respect to our lecture notes. Right. Right. Thank you all of you. Please message me if you have any doubt. Who is that 1B4? Ashwita, cut down the rule number of 1B4, okay? Cut down the rule number of 1B4 and send me the attendance. Okay, thank you all of you.